Hello and welcome to another Algebra 1 lesson by eMath Instruction. My name is Kirk Weiler and today we'll be doing Unit 4, Lesson 8 on piecewise linear functions. It's a very impressively long name, piecewise linear functions, but I think that you'll understand them, especially given all the work that we've done in Unit 4 so far on linear functions and graphs of lines. So let's get right into it and talk about what a piecewise linear function is. All right. So sometimes the formula for a function is different for different intervals of its domain. In other words, we've all seen functions now at this point that come in with formulas, right? But sometimes we want the rule to be more complex than just one formula. We want one formula to apply for these x values and then a different formula to apply for these x values. And sometimes piecewise functions can be complex enough that they have many formulas involved. We're going to be primarily working with piecewise functions that just have two formulas involved. Now, when each of the formulas are linear, i.e. they're y equals mx plus b, right? Then we call this a piecewise linear function. Each piece is linear. So let's take a look at one where we have its graph to begin with and we think a little bit about the behavior of this function. Let's take a look at exercise number 1. A piecewise linear function f of x is shown graphed below. Answer the following questions. Letter A, evaluate each of the following, f of -3 and f of 9. All right, so evaluating a function based on its graph that we have here, right, is something that you've done many times, and there's nothing in letter A that is really any different than what we've done at all so far. So I'd like you to pause the video at this point and see if you can fill in what f of -3 is and what f of -9, or what f of 9 is. All right, always keep in mind that the number that's sitting inside of the function here is the input, it's the x value, and what the function is equal to is the output, or the y value. So for f of -3, all I'm going to do is go over to -3 on my graph. I'm going to go up to this point, right, and that's the point -3, 2, and therefore f of -3 is just equal to 2. Likewise for 9, I'm going to go over to 9 on my x-axis. I'm going to go down to the curve, which is right here. That's going to be the point 9, -2. So f of 9 is -2. Don't take any significance out of the fact that one of those is +2 and one of them is -2. I'm not trying to make any point there whatsoever. All right, but now let's get into something that's more important. Letter B. Is f of 0 equal to 4? Or is f of 0 equal to 8? How can you tell? So I'd like you to pause the graph now. I'd like you to pause the video now. Look at the graph and try to think about which one of these it's equal to. And side note, it can't be equal to both, right? Because the golden rule for functions is when you have an input like 0, there can be one and only one output. So it's either going to be 4 or it's going to be 8, but it's not going to be both. And I'd like you to take a look at this and think about which one it should be. All right, so what we're really kind of deciding on, right, is are we looking at this or are we looking at that, right? Which one are we talking about? This one or this one? And the answer is f of 0 is equal to 8 because that point is filled in. Maybe I'll put a little quotes around filled in. Now, if you think about this, you should be very comfortable with this from graphing inequalities. And remember, when we graphed an inequality on just a single number line, right, we indicated when a value wasn't there by putting an open circle, and we indicated when a value was there by putting in a filled in circle, a filled in point. So basically what we're saying is at this transition point, at x equals 0, when we transition from one line to another line, the output is going to come from this line, and then once we have that output, we jump down to this line and we continue to get outputs then from that one. All right, let's keep working with this thing. Now, something that we want to be good about being able to do is when we're given graphs of lines, and we do have graphs of lines here, we want to be able to come up with their formulas. So let's take a look at letter C on that. Give equations for this function for the following domain intervals. One of them for x less than or equal to 0, and one of them for x greater than 0. All right, so just to be clear, right? For x less than 0, less than or equal to 0, we're talking about this portion. And for x greater than 0, we're talking about this portion. Now, I don't want you to worry so much about the fact that this line ends here and this line begins here. That's not what I'm so worried about, right? What I want to do is just think about what the equation of each one of these lines would be. Let's talk about the line up here first, and then let's see if you can think about this line more on your own. So if I take a look at this line, right, and I kind of think about it, I'm going to put it down here, in terms of y equals mx plus b, one thing I can tell for certain, right, is that my b is going to be equal to 8. My real question is what my slope is. Now for my slope, I just want to think about sort of rise over run, and I can take and look at points that are nice on this curve, and what I can see is that for every 1 unit I go over, I go 2 units up. 1 unit over, 2 units up. So my slope is 2 over 1, or just 2. That means that my formula is y equals 2x plus 8 for all those x values that are less than or equal to 0. And I could test this, right? I could grab a random x value. Let me erase these so that we can see it a little bit better. Like I could take the x value of -2, let's say, right? And I could take -2, and I could substitute it up into this formula. I'd get 2 times -2, which is -4. I'd then have -4 plus 8, which is +4, and that is in fact what the y value is when x is -2. Now what I'd like you to do is try to do the same thing for this line. Try to come up with its formula. Pause the video now and see if you can do that. All right, well, same thing. Let me just move this out of the way and kind of draw an arrow down here. Y equals mx plus b. Again, in this case, the b is very simple, right? Now you might say, well, that's got an open point there. I get that, but still, the y-intercept of that line would still be 4. The slope is a little bit trickier, right? If I take this point, and this point, I can see that for every 3 units I go to the right, I go 2 units down, right? 3 units to the right, 2 units down, which means my slope is a -2/3, and therefore I've got f of x equals -2/3 times x plus 4. Again, easy enough to test both of these formulas by grabbing x values that lie in the domain covered by that particular line segment or line piece, and just check to see if they actually give the correct outputs. All right, so it's very, very simple, right? We can have these rules, these piecewise rules that say, hey, for these x values, for all the x values that are less than or equal to 0, here's the rule that you're going to use to get your outputs. And for every x value greater than 0, this is the rule that you're going to use to create your outputs. It's just a little bit more complicated of a function rule than one where you're given just a simple single formula. Let's keep going and work more with piecewise functions. All right, now graphing a piecewise linear function can be challenging, right? Because you've got these 2 different equations. Keep in mind though, what you know about both the slope and the y-intercept of a line. It's very important that you keep that in mind. So let me show you the Euler method for graphing a piecewise linear function. Let's take a look at exercise number 2. Consider the piecewise function given below. F of x equals -1/2 x plus 6 for x less than 2, and f of x equals x plus 1 for x greater than or equal to 2. Letter A, graph the 2 separate lines that this function is based on, connect the integer points with dashed lines. All right, so let's talk about this a little bit, and let's maybe do the first one together. We'll have you do the second one. Notice I've put a y in front of each formula because that's truly what I'm talking about, right? Y is equal to this when x is less than 2, and y is equal to this when x is greater than or equal to 2. So let me tackle this one, right? Y equals negative 1/2 x plus 6. So, I'm going to just graph that line. I'm going to go up here to a y-intercept of 6, and then because the slope is negative 1/2, I'm going to go to the right 2 and then down 1, and right 2, down 1. Right? I should be able to graph this line very quickly using that. And now the directions say connect with a dashed line, and I'll explain that in a little bit, okay? But for now, I just want to do that, okay? Nice and dashed, okay? And really, I should have a straight edge, but we're going to save ourselves a little bit of time. Now what I'd like you to do is I would like you to graph y equals x plus 1 on the same grid, okay? Bring out these points, and then again, use a dashed line to connect the points. Pause the video now and go ahead and do that. All right, well, maybe I took the easier one, but one like this, you really need to be good about knowing that, oh, okay, m in this case, the slope is 1/1, right? So the y-intercept, right, that's easy as 1. Sometimes the slope of that line can be a little bit tricky. That's 1/1. So here we go. I'm going to go up to a y-intercept of 1, to the right 1, up 1, to the right 1, up 1, to the right 1, up 1, etc. I think that's enough for me to know what the pattern is. Oh, nice little tapping on the board. There we go. All right, so here's one of the keys in math. And you'll see this no matter how far you go in math. We'll see it in a lesson, just a few lessons down the line. Anytime you have a line that's graphed and it's dashed, it's almost like we're saying, it doesn't count. The dashed line is a guide, but it's not actually the points that are on the line, okay? So let's take a look at letter B. What is the value of f of 2? All right, well, this is very important. When you look at a piecewise function, if you're asked what is the value of f of blank, right? Well, you've got one of two formulas you're going to put it in. You're either going to put it into this formula and get an output, or you're going to put in this formula and get an output. And the only question is, which formula applies when x is 2? Well, this is only good for when x is less than 2. But this equation is good for when x is greater than or equal to 2. So bingo, that's my guy, right? So in other words, f of 2 is just going to be 2 plus 1, and it's going to be 3. Now, what I'd like to do right now is color that point in. If f of 2 is equal to 3, then 2 comma 3 is on this graph, right? If I go out to 2 and I go up to 3, that thing is on the graph, and then this point is not on the graph, right? So I want you to, based on this calculation, put in a nice heavy filled in point there and a nice open circle there. Now, how do we fill in the rest? Well, let's take a look at letter C. Draw over the dashed lines with solid lines for the domain intervals indicated by the formula. Okay, so now I want it to count, right? So the dashed lines, again, don't really count. Okay, at this point, I basically have this point, and that's it. Now, what do I know? Well, I know for x less than 2, it should be this formula. Now, x less than 2 are all points to the left of 2. In other words, I should fill in this portion of the curve. All right? Now, for x greater than or equal to 2, it should be this particular curve that counts, this one right here, right? So I'm just going to fill this one in. And that's it. Now, I could go back if I wanted to make my graph look nicer, and I could erase the dashed lines, but I don't need to. Dashed lines indicate that those points are not actually part of the function, they're just a guide. So if you want to, if you're like one of those people that like does your graphs in pencil, and really wants to make them look nice and neat, then at this point you could come in and you could go, all right, I'm just gonna get rid of that dashed line, and I'm gonna get rid of that dashed line, and maybe get rid of like that little bit in there. And there you have it, right? And that's more similar to the graph that we saw in exercise number 1, but there is really no need to do that. You can leave those dashed lines. I mean, I could have like a random dashed line somewhere down here and it wouldn't matter, because dashed lines don't count on graphs. They are not part of the graph. All right, let's keep going. Now, in both exercise 1 and exercise 2, in each example so far, the piecewise function has been discontinuous at the points where the formula changes, meaning that it literally jumps from one point to another point that aren't connected. Now, this doesn't have to be the case, and in most real-world applications, it isn't the case. In most test questions, it is, but in most real-world applications where there are piecewise linear functions, they are nice and continuous. So let's take a look at an example of that right now. Let's take a look at exercise number 3. For the piecewise function below, do the following. F of x equals 2/3 times x plus 2 for x less than or equal to 3, and f of x equals negative 2x plus 10 for x greater than 3. Letter A asks us to graph the piecewise function using the technique described in exercise number 2. All right, great. So why don't you go ahead and try that technique that we just did, graph both of these two linear equations, right? Y equals 2/3 x plus 2, y equals negative 2x plus 10. Draw everything in dashed and then kind of color in the portions that apply, x less than or equal to 3 for this one, x greater than 3 for that one. All right, and then we'll take a look. So pause the video now and take a few minutes to do that. All right, let's take a look. So for our first one, y equals, let me just, whoops, I don't know what just happened there. That was cool. Let me just erase that. I had a little jump in my board. So we're graphing y equals 2/3 x plus 2, right? We have a y-intercept at 2. We have a slope of 2/3, so we're going to go to the right 3 and up 2, right 3, up 2, right 3, up 2, reverse the trend, down 2, left 3, etc. So I'm going to, nice dashed line there. All right. Then y equals negative 2x plus 10. I'm going to have a y-intercept at 10. So maybe just be consistent here, Kirk. Y equals 2x plus 10. Now I'm going to go down 2 to the right 1. Down 2 to the right 1, down 2 to the right 1, etc. All right, let's get that in there. Nice dashed line. Okay, and now my final piece is, I look at this formula and say, well, this formula applies when x is less than or equal to 3. All right, so that's going to be this one. It's going to apply everywhere in there, right? And then this formula is going to apply for every x value greater than 3. So that's going to be right in here. And again, if you really feel the need, you are welcome to then erase this portion of the dashed line and that portion of the dashed line. Nothing wrong with doing that, but it's not absolutely necessary. Now, what you can see is in this problem, unlike the first two, there is no jump, there is no open circle, right? At that transition point of x equals 3, the graph is nice and continuous. So why is that? Letter B asks us, why is the function continuous at x equals 3? What do you think? Write something down. Well, the reason is very simple. At x equals 3, even though this formula doesn't apply at x equals 3, only applies for x greater than 3, both of these two formulas give me the same output. Here, let me show you, right? So f of 3, right, which is definitely 2/3 times 3 plus 2, those would cancel, give me 1. 2 times 2 is 2, plus 2 is 4. And now this one really isn't f of 3, but I want to show it in terms of that other formula, right? Negative 2 times 3 is negative 6, plus 10 is equal to 4. right? So both formulas have the same output. Right? It's when, at that cutoff point, when we go from one formula to another, right? If they've got the same output at that x value, then the two lines will meet up, right? They will just meet up nice, right? They'll give you a nice turning point, maybe, something. But when they have different outputs, as they did in the first two exercises, then you get what's called a discontinuity, right? It's discontinuous between one formula and another. All right, let's do one more problem. Here we go. Now, piecewise linear functions can be particularly useful in modeling a variety of real-world shapes that are made up with line segments, okay? So there's lots of situations in the real world where you've got a couple line segments that are matching up at a particular point or something like that, right? And you want to model it mathematically, okay? Piecewise functions are wonderful for this. So let's take a look at exercise number 4. A roof has a side profile as shown in the graph below. Letter A, at what x value will the function that describes this profile change from one formula to the next? All right, this should be simple enough. Pause the video now and see if you can figure out the x value where one line segment sort of transitions to the other one. All right, well, hopefully it's pretty easy, right? It's right here, right? So at x equals 6, that's going to be kind of the cutoff where, one formula switches over to the other formula. Granted, they're continuous there, right? They have the same y value, but still there's going to be a transition. Now, letter B. What is the formula for the line segment to the left of the value you stated in A? You should be able to do this graphically. All right, so I'd like you to do this on your own, but come up with the equation of this particular line. All right, you should be able to do that because you can see what its y-intercept is. You should be able to figure out its slope graphically. Go ahead and come up with that. Just write it down in terms of y equals mx plus b. Pause the video now. All right, well, let's do it. So I've got, y equals mx plus b, all right? Well, what do we know? Well, we know that the y-intercept is 7. All right, so it's going to be something plus 7. And now my slope, right, I can figure out by taking some nice points on this curve. It looks like for every 3 units I go to the right, I'm going to go 1 unit up. So that means my slope is going to be 1/3. So the equation of my line for all the x values that are to the left of that cutoff point is going to be y equals 1/3 times x plus 7. Now, coming up with the equation of this one is much harder, right? And think about why that is. It's harder because we can't just see the y-intercept. The y-intercept, to figure it out graphically, you'd have to extend that line and it would be somewhere up there. And we'll figure it out in a moment. But first, let's take a look at letter C. What is the slope of the line segment to the right of the value you stated in A? So this is just my way of sort of getting us going on coming up with its equation. What is the slope of that line segment? Pause the video now and see if you can figure that out. All right, well, it's one of the most important slopes that's out there, okay? And this is one that you want to just sort of know automatically, right? Here we go to the right 1 and down 1, right 1 and down 1, right 1 and down 1. And so my slope in this case is -1 divided by 1, or just -1. All right, so it is very important, right? When you see a line segment that goes through the diagonals of the boxes and it's increasing, then I've got a slope of 1, positive 1. And if I see a situation like what I have in this problem, that was kind of cool. When I see a situation like what I have in this problem, where the line segment is going down and through the corner of the boxes, then my slope is -1. all right, which you can't see because it's covered up by that. All right, let's keep going and figure out what the equation, I did it again. Figure out what the equation, I don't think I've ever done that, and now it's happened twice in the span of a couple minutes. Let's take a look at letter D. Determine the equation of the line segment to the right of the value in letter A. Okay, so how do we do this? Well, this really takes us back to a skill that we learned a few lessons ago, which is just simply how do you write the equation of a line when you know 2 points that lie on that line? Well, our first step was always to come up with the slope. Thankfully, we've already done that. And we could have done that by taking these 2 points and just coming up with them. In fact, those 2 points are 6, 9 and 9, 6. Interesting. All right. And we could have come up with, a slope of -1. But remember, what we do now is we put that slope into our y equals mx plus b format, choose one of the 2 points. I think I'm just going to take the first one. We got to be careful here, putting in 9 for y and 6 for x. This will allow us to solve for the y-intercept. Add 6 to both sides, and I find my y-intercept is 15. So the equation of my line, which I can just barely put in here, is y equals -x or -1 times x, that's up to you, plus 15. Now, by the way, I should feel relatively comfortable with that as my y-intercept, because if I took this line and I sort of extended it, right, and I extended my y-axis, negative or positive 15 seems about right. Had I gotten something like a y-intercept of 3, or maybe I made a mistake here, yeah, that's what I would have gotten. Let's say I subtracted 6 from both sides. I would have gotten a y-intercept of 3. Well, there's no way that's happening, okay? So that's now my formula for that particular line segment. So I have these 2 formulas, right? This one is y equals 1/3 x plus 7, and this is the formula for that. So now let's talk about letter E. Write the equation of the piecewise function, include the intervals over which the 2 formulas apply. All right, so let's write the formula of a piecewise function. This is kind of cool, right? Here's how you do it. First, we write down f of x equals, and then we have these big old brackets that look very similar to set notation. Okay, now we're going to write down our 2 formulas. Okay, one formula, 1/3 x plus 7. Our other formula, -x plus 15. Okay, now we have to decide on their domain intervals. Well, the first one, and let me kind of get rid of this stuff so we're not getting it all complicated, right? This first one starts at -3 and ends at 6. So I'm going to put down -3 is less than or equal to x, which is less than 6. And now my other one goes from 6 to 9. So I'm going to do 6 is less than x is less than or equal to 9. Now, I have one last thing I have to do though. I have to decide, because there's no open circle here, whether or not I'm going to put the equal sign on that 6 or on that 6. Now the question is, which one do I need to put it on? And the answer is, you could put it on either one of them. All right, either one of them. Technically speaking, and I would get a lot of flack from this from some math teachers, you could put it on both. You just can't put it on neither. Because if I didn't have it on either this 6 or this 6, I'd have to have an open circle there. But you could have it on this 6, you could have it on that one, right? Or you could have it on both because it's continuous. If we had a situation like in exercise 1 or exercise 2, where there was an open circle on one line segment and a closed circle on the other one, then we would put the equal sign on whichever one had the closed filled in circle. On this one, they're in a certain sense, they're both filled in. So I'm just going to put it on the first one, right? So I'm going to say -3 less than or equal to x less than or equal to 6. This one I'm going to say 6 is less than x less than or equal to 9. All right, one last little piece to this problem, then we'll wrap up the lesson. Let's take a look at letter F. The architect designing the roof would like to place a reinforcing beam at a height of 7 feet above the floor. She decides to model this beam using the equation y = 7. If she does not want the beam to extend outside the roof, what are the x values where her beam should start and stop? Illustrate on the graph. Awesome. Okay, I'd like you to pause the video now and see if you can kind of sort through what's going on in this problem. All right, well, we talked about horizontal and vertical lines in the last lesson. All right, so y = 7 is a horizontal line, which is good because this is a horizontal beam that she's designing in here. All right, and in fact, y = 7 would be a horizontal line that looks like this. Okay, so that would be that horizontal line y = 7. But keep in mind, it says she does not want the beam to extend outside of the roof. So what are the x values that the beam should start and stop at? Illustrate on the graph. Well, if I don't want it to extend outside of the roof, then I want it to start here. I want it to stop there. Maybe I'll erase the rest of this. So I want it to start at x = 0 and end at x equals, I guess that would be x = 8, right? And that would be it, right? If you said it goes from 0 to 8, that would be fine. If you used interval notation, if you did something like this, that would be kind of great too. But really, it says where does it start and stop? Well, it starts at x = 0 and it ends at x = 8. All right, let's wrap this up. So all along, right, we've talked about functions as being rules that give outputs when you are given an input. Nobody ever said that those rules should be easy or simple or anything like that. You know, a function is simply a rule, however simple or complicated, that gives you an output for a given input. Piecewise functions, not just piecewise linear, but piecewise functions are more complicated rules. They say, hey, look, for these x values, use this formula. For these x values, use this formula, etc., etc. One of the most complicated piecewise functions that people kind of run into on a yearly basis is the piecewise function that calculates your income tax based on how much money you make each year. That is actually quite a complicated piecewise formula, but it basically says something like, well, if you make $0 to $15,000, use this formula. If you make $15,000 to $25,000, use this formula. If you make from $25,000 to $50,000, use this formula, etc., right? And again, piecewise functions come up all the time in the real world, not just with taxes, but in situations where, you know, you've got geometric shapes like what we had in the last particular problem, and you want to model those using line segments and using formulas, right? A single formula isn't going to get the job done, so you have to have this formula that comes in pieces. All right, we'll work more with a specific type of piecewise function in the next lesson. For now, I just want to thank you for joining me for another Algebra 1 lesson by eMath Instruction. My name is Kirk Weiler, and until I see you again, keep thinking and keep solving problems.